All right, so welcome back. We are now in week 7. That's what this is, what, lecture 12, I believe? No, maybe even 11. Well, we finished 6 weeks, which is 12 classes, but one of them was the test. And one of them, yeah, this one was the test. Huh? Yeah, but the reviews are still called lectures. So, whatever we are, I don't even remember. Whatever. So, how far can I go? So, about here. Okay. So, back to math 140. Lecture, who knows? I think 12, question mark, I don't know. And now we start chapter 11 on probability. Probability is so much fun. I really enjoy probability. No, I really am not. And if you look at the different branches of mathematics, I really enjoy almost all of them. But probability is a lot of fun, I find, because there's a lot of counterintuitive results in probability. One of my favorite is the following example. It's got nothing to do with this class. If you don't pay attention for the next 3 minutes, you'll be fine. But I think it's interesting. Let's imagine you have a bunch of people in a room, a large room, lots of people coming in. And suppose, for the sake of this example, there's no such thing as February 29th. So everyone has one of the normal 365 birthdays. How many people have to be in a room for there to be a 100% chance that 2 of them have the same birthday? How many people need to be in a room under those conditions that I just provided for there to be a 100% chance that 2 of them have the same birthday?
58.
How much? 58? I can have 58 people, all different birthdays. Huh? A lot less than that. 2 people. If you and I are in the room, are we 100% sure that we're going to have the same birthday? No, it's not a true. This is not a hard question. Yes? No. 3, not 65. If there's 365, we can all have different birthdays. It's 366. The first 365 people can all have different birthdays. The next person walks in, it's got to pair up. There's only 365 birthdays to go around. So for there to be a 100% chance that 2 people have the same birthday would require 366 people to be in a room. For there to be a 0% chance that 2 people have the same birthday, what's the maximum number of people that can be in the room? 1. Because as soon as the second person comes into the room, there's always a chance that they have the same birthday. So the question is, how many people must be in a room for there to be a 50% chance that 2 of them have the same birthday?
Isn't it like 23 or something?
It is 23. It is 23 for no apparent reason other than the laws of mathematics, the laws of probability. But it turns out that there's 23 people need to be in a room for there to be a 50% chance that 2 of them have the same birthday. Very unintuitive. Most people guess. I mean, you obviously have known this already because you said, isn't it? In other words, you've seen it before. So thanks for ruining it for everyone else. Off camera. Okay. But for there to be a 50% chance that 2 of them have the same birthday, most people guess about 180, 183. They guessed right in between. This is called the birthday paradox. And we're not going to explain why it's 23. I only bring this up as an example to illustrate that sometimes the rules of probability are very unintuitive. And you have to make sure that you just follow the rules, the axioms, and you don't go off on, well, I think it's, or it seems to me that it's this. Just follow the rules and you can answer just about any question. Well, certainly any question in this course can be answered with the very basic rules. We don't even have to get to more advanced rules. Very, very straightforward rules. You had a question for a second? Well, I think there's more than 23 people here. But if you like, we can do the experiment. We can go around and everyone says their birthday very quickly and see if anyone doubles up. But I just don't want to. So only in the interest of time, because we have what to cover today. So again, I only bring that up as an illustration that the rules of probability must be followed until you become a master at probability. Then you know when you can deviate from the rules and do things on your own. So, what are the basic rules of probability? Well, for one thing, we are only concerned about situations where an experiment is performed and we do not know in advance what the outcome is going to be, but we do know all possible outcomes. Can someone give me an example of either basic or complex, but basic is usually better? An example of a situation we perform some experiment. And when I say experiment, I don't see like Bunsen burners and, electron telescopes. Just you do some kind of action where you're looking for a result and you do not know what result you're going to get, but you do know all the possible results that you might get. Let's just give it more basic than that. Yes. Rolling a die. It's flipping a coin and rolling a die are two of the most basic situations. If I roll a die, I do not know, here's 2 and here's 3. I do not know in advance what I'm going to get, but I do know what I might get, right? What are the possible outcomes if I roll one die? Well, not 1 out of 6. What are not 1 of 6? 1 through 6. The outcomes are 1 or 2 or 3 or 4 or 5 or 6. If I flip a coin, what are the outcomes? Heads or, well, not 1 or 2, but heads or tails. I mean, unless you make your own die and it has a 1 on one side and a 2 on the other, which, by the way, is not a horrible idea because you can't do math with heads and tails. And you could do math with a 1 and a 2. So I actually prefer a 1 and a 2 for a coin, or even a 0 and a 1. Okay, so now let's go a little more complex. The birthday example is too complex. Let's just keep it more basic than a simple thing like this. Can anyone think of any other scenario where an experiment is performed, an action occurs, and we do not know what the result is going to be, but we know what it might be?
Rock, paper, scissors.
You mean like which one you're going to do in particular? Sure, there's 3 outcomes. We don't know in advance which one it's going to be. Anyone else? Try again. Certainly an RNG, yes.
What about what shoe you like to put on first? An experiment to see what shoe.
You mean left or right?
Left or right, yeah.
So you're doing a social experiment. You wonder what people do first.
Yeah.
So you pick a random person, you video record them without watching in the morning, and you see if it's going to be left or right foot. Perfect. No ethical problems with that at all. Yes. Blackjack, card games, sure. Slot machine.
Like marbles.
In a bag, sure. Having a child, boy or girl. Is it going to rain tomorrow here at Northridge? Yes or no? A lot of times we think of experiment as something that you do. But with the raining situation, you're not doing anything. Is anyone doing it? Well, God, the great turtle in the sky, whatever you believe. But the point is that quite often actions are being performed, not necessarily by you, but you're curious what the outcome is going to be. And more specifically, what we're concerned with is how likely each outcome is. So if I flip a coin, what's the likelihood that it comes up heads or tails? 50% if it's a fair coin. If it's fair. How do you know if a coin is fair? How do you test it? You weigh it, well, how do you test it? Flip it a bunch of times and then see what the result is. So let's say I flip it 10,000 times and I get 10,000 heads and no tails. Do I know for a fact that it's not fair? For a fact? There's no chance I could just be extremely unlucky. No chance. It's highly unlikely. It's highly unlikely if I flip a coin 10,000 times, the coin is fair. It's highly unlikely that it comes out 10,000 times heads, but it's possible. This is the big idea of leading into the next few chapters. The difference between a possible event and a likely event. I cannot definitively conclude a coin is not fair if I flip it 10,000 times and it comes up heads every time. But I certainly have beyond a reasonable doubt. Okay, there's certainly a likelihood, a threshold of possibility that once I pass it, I conclude, sorry, this is not fair versus it is fair. Would flipping it 10 times and getting 10 heads be enough to conclude that it's not fair? Well, actually, by the rules that we're going to come up with, yes. Even 6 or 7 times will be enough for us to conclude that it's not. I think even more than less than that. I think even 5 times might be enough by what we're going to develop as we go along. What we're going to develop is that essentially anything with less than a 5% chance of occurring that does occur is going to make us question our beliefs. That's going to be our basic threshold. If there's less than a 5% chance of occurring, oh, you say the coin's fair? Okay, let me flip it a bunch of times. I get a result that's less than a 5% chance of occurring if the coin is fair. That's going to make me say, sorry, this coin is most likely not fair. I'm going to switch to the other team there. But in order for us to calculate how likely that particular outcome is, we have to develop the rules of probability first. And the rules of probability that we're going to develop are very, very basic. First, the definitions. A random experiment is an experiment whose outcome is not known in advance. Whose outcome is not known in advance, but all possible outcomes and I'm going to write in parentheses the set of which is called the sample space. Is known. So a random experiment is one whose outcome is not known in advance, but the collection of all possible outcomes, called the sample space, is known. So flipping a coin, rolling a die, having a child, whether it rains, all those examples that we talked about. Those are all random experiments. And we're interested in developing the basic rules of probability on these random experiments. So an event is any subcollection of the sample space. Those are our basic definitions. Random experiment, sample space, and an event. So somebody give me an event for one of those examples that we spoke about a few minutes ago. Pick any one of our examples and give me an event for that example. I'll start. Rolling a die, my event is getting an odd number. Is getting an odd number a subcollection of the sample space for rolling a die? What was the sample space for rolling a die again? I forgot. What's the collection of all possible outcomes when I roll a die? 1, 2, 3, 4, 5, 6. Is rolling an odd number a subcollection of that? Yes, 1, 3, or 5. So the event that I just described is getting a 1, a 3, or a 5 when I roll a die. It is a subcollection of the sample space.
So then for the cars, it could be, to get a heart.
So what is your experiment? You're picking a card from a deck of cards?
Yeah.
Okay, so getting a heart would be an event. How many outcomes in the deck would correspond to that event?
There's 12 out of 52, so
There's how many?
12 hearts,
Okay, don't play cards.
right? Or
There's 13,
with the
right? In my day, before we had this proliferation of cell phone and computers, we actually spent a lot of time playing cards as kids. Do you guys, in general, have this experience in your generation? I literally don't know, of playing cards? Okay, so, I mean, I've actually had students where I put a question on a test about cards and they didn't even know what cards were. Or at least they claimed they didn't know what cards were. I don't know if that's true or not. But there are 13 cards of each suit, 1 or ace through 10, and then 3 jack, queen, king, 13 cards. So the event getting a heart is certainly a sub-collection of the event of all outcomes of the sample space. How many outcomes are there of the sample space? 52, right? Any one of the 52 cards will be my sample space, and getting an event, getting a heart will be the event. There are 13 of them. Anyone give me another example? Yes. Flipping a coin and having a land on tails. Okay, that event happens to be one of the outcomes. That's fine. Hello there. So usually when we talk about events, we talk about collections of outcomes, but one outcome is certainly a collection of outcomes itself. So one outcome is perfectly fine. Over. Okay, so a probability model for the experiment is a valid, and I'm going to put this in quotes right now because we haven't defined what a valid, what I'm going to write next yet. So it's a valid assignment of probability to each outcome. Okay, a probability model is when we assign each outcome a probability in a valid way. And what makes the assignment valid are our basic rules of probability. So give me a probability model for flipping a coin. Okay, if I give you a coin, right? Here's a coin. I give you a coin. I say, give me a probability model for that coin. I flip a coin. It's either heads or tails. I want to assign a probability to heads, and I want to assign a probability to tails in a valid way. Give me an example. 0.5, 0.5, 50%, 50%. Right? That's a valid assignment. If it's a weighted coin, maybe I'll assign it 0.7 and 0.3. Could I assign it 0.2 and 0.5? Okay, so we have our first rule that makes the probability model valid. Is that the probabilities have to add to what number? 1, because it has to be one of the outcomes. Right? By definition, it has to be one of the outcomes. There's no other possible results. So rule number 1 of a probability model is that the probabilities must add to 1. This, of course, is for basic probability models that are not they're not continuous. We're going to get to continuous models. If you're waiting for the bus, and the bus is going to come anytime between now and 10 minutes from now, how many outcomes are there for the bus for when it comes? No, it's going to come anytime between now and 10 minutes from now, but I don't know when. And that's what I'm interested in. When the bus comes, that's my experiment. How many outcomes are there for when, how far from now, how long it will be until the bus comes? Not even a second. How about a half a second? How about a tenth of a second? How about a millionth of a second? So if you get down to it, in theory, there's infinitely many solutions, right? So when you deal with a case like that, where there's infinitely many solutions, but they're all really small, then you have to go to the rules of calculus to do it. And for those of you who've had calculus, it's not the sum that has to equal 1, but rather the, who here said calculus? Anyone? The integral has to equal 1. But for our basic cases, rule number 1, the sum of probabilities must be 1. When you add up all the likelihoods of all the events, the first rule of being a valid probability model is they have to add to 1. Does anyone think of another rule? Because if not, I'll give you a possibility. And as far as you're concerned, if you have no other rules, it'll be valid. Okay, so the other one is no probability. The probabilities cannot be negative. That's it, those two. Any probability model that satisfies those two conditions is valid. A valid probability model. Whether it conforms to reality is something else. If I give you a coin and I say 0.5, 0.5, 50, 50, maybe it's a fair coin, maybe not. I don't know. Anyone here a basketball player? Okay, I want you to go out and I want you to shoot free throws. No, half court shots until you, no, full court shots until you make one. Full court shots until you make one. Is that a valid random experiment? Why not? I don't know how many shots it's going to take, but it's either going to be 1 or 2 or 3 or 4 or 5 or 6 or 6 and so on, right? What's wrong with that?
Because each time you will get like, first time you will get like 30 shots, maybe the next time you will get 10 to 1.
Wait. You're doing this one time. You are shooting from full court until you make one. And we are interested in how many shots it takes. The question is that a random experiment? And the answer is yes.
Because once you hit it, then you'll figure out.
Well, once you hit it, the experiment's over. I have my outcome now.
That's what I'm saying. And
Right?
that'll give you the probability of following.
Well, we'll get there in a minute, but I'm saying like if you take 7 shots, the answer is 7. That's the outcome. Right?
So if you did it,
If I did it in 1, I did it in 1. Right? Snake Plissken did it in 1. Anyone? Huh? I don't think LeBron James hit a full court shot.
Yeah, but I didn't do it, but like,
Well, they all do it at some point in their life. The king, thank you. Anyways, no, you got me monologuing. Listen, here's the idea. For that example, do we know the probability of him making it on the first shot? Or the second shot? Or the third shot? Or the fourth? Or the fifth? We don't actually know any of those probabilities. And how many are there? How many possible outcomes are there for that experiment? Infinitely many. You can't stop and say, well, it's got to be among the first 100. Well, no, I might miss all my first 100 and go to 101. Okay, well, it's got to be that. Well, no, I might miss that too. There's no number where you stop it and say, it's got to be before this. So there's infinitely many outcomes. And the question is, how do you assign a probability to each one and have it add to 1? You can do it. It's not hard. Whether it conforms to reality is something else. Anyone know, by the way, how to add together infinitely many positive numbers and get 1 as a result? Anyone know? How can you add together infinitely many positive numbers and get 1 as a result? Well, okay, so you have calculus then. Well, not exactly that, but here. Take the number 1/2. You don't have to write this down. This is just for fun. Take the number 1/2. And I want you to imagine that you're crossing a room and the 1/2 represents that you just crossed half of the room. And then I want you to cross half of what's left. How much? 1/4, right? Half of what's left. You just crossed half of what's left. And now I want you to cross half of what's left. 1/8. And now I want you to cross half of what's left. 1/16. And I want you to do this over and over and over again. If you go after a million, after a billion, after a trillion of these steps, where will you be?
Close to one, but
You'll be close to 1, right? And the further out you go, the closer to 1 you get. So in the language of mathematics, we would say that this series converges to 1. It gets closer and closer and closer and closer to 1 the further out you go. You'll never get there, of course, if you ever stop at some point. But from a mathematical standpoint, this becomes that. So if I assign my first throw a 50% chance, and then my second throw a 25% chance, and then my third throw a 12.5% chance, and so on, then I can assign each of them a positive probability, even though there's infinitely many outcomes, and have it add to 1. Whether it conforms to reality, that's a whole other issue, but I could do it. In this class, we will not be doing that, okay? I just want to give you these concepts to deepen your understanding of what we're doing, but the examples that we're going to do are very, very basic in comparison, okay? So any questions so far, just conceptually, on what a probability model is?
When exactly do you, based off the fractions, when do you add the decimal or what you're talking about to make it equal?
Well, those all were decimals.
That's what I'm saying, but, when do you stop, like, how do you finalize? So you go on.
You never actually get to 1 in a finite amount of time. It's the idea that the further out you go, the closer to the 1 you get. So that if you include all of the infinitely many possibilities, it's equal to 1 in a mathematically precise way. Okay, so let's list our basic rules of probability. We already have the first two in terms of what creates a probability model. Each one of these will hopefully be obvious. Maybe not obvious before you see it, but once you see it, it should be obvious. No matter what event you give me, the probability of that event occurring is always snug between 2 numbers. What 2 numbers is any event in the history of time between 0 and 1? Either there's a 0% chance that it occurs, there's a 100% chance that it occurs, or something in between. So the first rule of probability club, don't talk about probability club. The second rule is the probability of every event is between 0 and 1. I cannot tell you how many times I put probability questions on tests when I teach this course or more advanced courses, and I ask for probabilities of outcomes, and I get numbers above 1 or less than 0 with no little notes saying, okay, I know this can't be right, I just don't know where I went wrong. If you ever in my class get a probability that's not between these 2 numbers, and you don't say, this is the problem, I just don't know where I'm going wrong, then you will not get partial credit for that. Okay, for that question. Okay, this is the most basic one. Any probability that I ever ask you to calculate must be between 0 and 1. That's rule number 1. Number 2, what is the probability of getting something in my sample space? 100%, because my sample space are all the outcomes. The sample space is the collection of all outcomes. So the probability of getting something in my sample space better be 100%. If it's not, that means we left something out, which means it wasn't the sample space to begin with. All right, so that's rule number 2. Rule number 3. I'm going to erase this. Rule number 3. If events A and B are disjoint. What does that word mean, disjoint?
The events don't go together.
go together, it's not quite clear. I'm looking for something a little more refined than that. Okay, I like that a little better, but still, it's not what I'm looking for, something a little more descriptive. What does it mean for two things, even in English? Forget about math for a second. What does it mean for two things to be disjoint? Maybe there's more than one definition. But things that are in math are disjoint if they have nothing in common.
No correlation.
No, correlation is a very specific mathematical term which doesn't apply here. Okay, correlation is a very, we had this earlier chapter, right? It's a mathematical value. Disjoint means that they cannot both occur at the same time. Rolling a die and getting either even or an odd. The event even and the event odd are disjoint. They cannot both occur at the same time. How about odd or prime? Is that disjoint?
No.
No, why not? Because I can get both at the same time. What number for rolling a die is both prime and odd? 3 or 5. How about even or prime? Is that disjoint? Why not? What do they have in common? How can you get both an even and a prime at the same time? 2. 2 happens to be both even and prime. So disjoint means they cannot both occur at the same time. So if events A and B are disjoint, then what's the probability of getting A or B? No, not A and B. If it was A and B, it's 0%. I can't get both at the same time. Huh?
50?
No. It's not a number because I don't know what A and B are. Okay, I'm not looking for a number here. I'm looking for a mathematical formula that connects this to something else that's equivalent to it.
1 minus b of a or 1 minus b.
No. So the answer is, you just do probability of A plus probability of B. If you have if you have events that are disjoint, if you have events that have nothing in common, and I ask you for the probability of one or the other, then you can just do them separately and add them together. So for example, if I say the probability of getting a heart or a club. If I say pick a card from a deck of cards, 52 cards, what's the probability of getting a heart or a club? Well, if I do it directly, out of the 52 cards in my deck, how many of them are hearts or clubs? Thank you. How many of them? 26. And if I did probability of just hearts out of 52, and if I said probability of just clubs, and I add them, do I get the same thing, right? When they're disjoints, you can just do them separately. Probability of hearts plus probability of clubs. You can just do them separately, right? Yes, no, maybe so? That's the maybe so one. Yes,
Can you give another example?
sure. Probability of diamonds or spades? Okay, how about probability of getting a 2 or 3 or a 5 or 6 when I roll a die? Well, 2 or 3 or 5 or 6 has what probability of occurring? How many of my 6 outcomes are either a 2 or a 3 or a 5 or a 6?
1.
4, 2, 3, 5, and 6. 4 of those outcomes. And if I just did 2 or 3 by itself, 5 or 6 by itself, add them together, I get the same thing, right? Same thing. So this is equal to probability of getting a 2 or 3 plus the probability of getting a 5 or 6. This only holds for when they are disjoint. Let's do an example where they're not disjoint and see that it does not succeed, this formula. Can I erase the 2 examples here? What? Thanks. What's the probability of getting a heart or a king? The probability of getting a heart or a king if I take one card from a deck of 52 cards. Well, first, the denominator is 52. I wrote that immediately because how many possible outcomes are there? 52. It's a little more than just being 52. There's another nuance there that I haven't mentioned. It's not just 52. There's one other aspect of this experiment which allows me to do it this way. What allows me to immediately put over 52? It's not just that there are 52 outcomes, because I can certainly do an example where there's 52 outcomes and it's not just over 52. Let's do a simple one. Raining or not raining tomorrow. How many outcomes are there? 2. Is it 1/2, 1/2? There's 2 outcomes. Is it automatically 50-50? Really?
No,
There's a 50% chance it rains every day? Every day, if I ask you what's the chance that it rains tomorrow, 50%, because there's 2 outcomes. It's not just the number of outcomes, there's one other aspect to it that's necessary for me to do over 52. What is that fact? No. They're all probabilities. Everything's probabilities. No.
The sample space?
No. Every experiment has a sample space. It's the fact that those 52 outcomes are all equally likely. I could get any card of the deck with the same chance of any other card. They are equally likely outcomes. When I roll a die, the 6 outcomes are all equally likely. When I flip a coin, they're all equally likely. The only time I can immediately go and do over the number of outcomes and just count how many ways that can occur and get my answer is if they are equally likely. Of those 52 equally likely outcomes, how many of them are hearts or kings? 16. How many of them are hearts? How many of them are kings? 4. H and K obviously standing for hearts and kings. So in this case, why is it that that formula from before does not work?
Because our outcome is not the same.
No,
It's not the same percent of chance to get the king.
no, that's not why. It's because they are not disjoints. There's an overlap.
Yeah.
Is it possible to get both a heart and a king at the same time?
Yes.
There's an overlap. You can't use this formula. Now, all is not lost. We have a follow-up formula, but I can't use this formula. This formula only holds when the events are disjoint, when they have no overlap. If you look at it in terms of a Venn diagram, here's event A, here's event B. This is the case when the events are disjoint. So if I want to calculate the likelihood of A or B, I can just do A, I can just do B, and I can add them up. There's no overlap. But what if there is an overlap? What if here's A and here's B? Then when I do A, I get not just the left part of A, but I get the right part of A. And when I do B, I don't get only the right part of B, I get the left part of B as well, which means I have double counted part of it. I've taken this part here in the center and counted it twice. So how do I rectify the situation where I count it twice, but I don't want it twice? I only want it once. Just subtract those outcomes. So in general, the probability of A or B is the probability of A plus the probability of B minus the probability of what? Minus the probability of what? A and B. Minus the probability of the overlap part of the A and B. That's what I counted twice. So remove it, subtract it off. No problema. So the probability of A or B. Now, this formula works for this one too. Because what is P of A and B if they're disjoint? 0. So this formula subsumes, is that the word? Subsumes, it's like it envelops, and I don't know, I don't do English well, but this formula is more general. It includes this as a special case. And the last property that we're going to do, the probability that an event does not occur, the complement of the events. Thank you. The probability of E complement, the probability that the event does not occur, is equal to what? Well, how can it be 0? The event, if the event E is getting an odd, then the complement of that is getting an even. You're saying there's no chance I can get an even when I roll a die? It's not going to be 0. How is the likelihood of getting the event E and getting the complement of the event E related?
What the complement?
Not getting it.
There's just be 1 minus B.
1 minus what?
1 minus B of B.
1 minus the probability of event. The probability of getting the complement of the event E is 1 minus the probability of getting E. Why? Because these two events, if you bring this to the other side, these two events, E and E complement, are disjoint. You can't have both E and not E at the same time. And together, E and E complement makes what? E and not E, the outcomes in the event E, the outcomes in that are not in the event E. When I look at all of them together, that becomes what? That becomes the, give a name for it. That becomes what? What? Don't guess nonsense. If you don't know, it's fine, yes? It's the sample space. It's the collection of all possible outcomes. And what is the probability of getting something in the sample space? 1. So this plus this has to equal 1. Yes? It says E complement, E superscript C. Different books will use different notation. I have seen a bar on top to denote the complement of E. I have seen a twiddle before E to denote the complement of E. I have seen that symbol. I don't even know what that's called. The negation of E, I've seen. There's no universal notation for the complement of E. Just make sure whatever book or text or website you're looking at, you understand the notation that they use. With these basic rules of probability, we can do lots. So let's do some examples. Let me know when you're ready, so I can erase you. Are you ready? Oh, I'm sorry, I'll get out of your way. Sorry. Are you sure? Okay. Oh, okay. 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 Example. You have any children?
Sorry?
You have any children?
Two.
2. All right, so let's look forward to the future. You have 3 children.
No thanks.
Too late. You have 3. How many you have? Boy and girl? Boy and girl. You have 3 children. We are interested in the number of girls. what are the possible outcomes for how many girls you might have? And again, basic probability, not any complications arising from the world that we live in, just boys or girls, we're going to keep it simple. 0.5 for boy, 0.5 for girl. How many possible outcomes are there for the number of girls that you might have? What are they? 0, 1, 2, or 3. So let's create a probability model. 0, 1, 2, or 3 are the possible outcomes for the number of girls that we may have. And what would I like to do now is I would like to assign probabilities to each of those 4 outcomes in a way that conforms with reality. If I don't want to conform with reality, I can make up whatever numbers I want. 0.1, 0.5, 0.2, and whatever's left. But if we try to conform with reality, then we are working under the assumption that having a boy or a girl is a 50% chance each. So the question is, what is the probability of having 0 girls if there's a 50% chance each birth of whether it's a boy or a girl, or 1 girl, or 2 girls, or 3 girls? Anyone want to give us a shot? Yes. No, you were here the whole time. I saw when you came back in. But good try though. Number of girls, probability of number of girls. We want these 4 numbers. What's the likelihood of getting 0 girls, 1, 2, and 3? Yes. How did you get that? Not saying you're wrong or right, but how did you get that?
Well, if there are 3 kids, there's 50% chance so now there's 2 possibilities.
Okay, then what would this one be? So you're saying, I'm not saying these are right or not, but you're saying this is 1/8, this is 1/4. What's this? Sorry? 1/4. And what's this? 1/8. What do those 4 numbers add up to? They don't add up to 1. Right? So those can't be the correct 4 numbers. That is not a valid probability model. They're not negative. Hey, you satisfied 1 condition. But unfortunately, they do not add to 1. Agreed? So now it turns out, just so you know, that 2 of those 4 are correct. Not going to tell you which 2, but and your logic also was correct. So here's how I would do it. I'd make a tree. Visualizations in probability are extremely useful. Your first birth, what are the outcomes for the first birth? How many outcomes are there for the first birth? 2. What are the possibilities? Boy or girl. If the first one was a boy, how many outcomes are there for the second one? 2. And what are they? Boy or girl. If the first one was a girl, how many outcomes are there for the second one? 2. What are they? Boy or girl. If the first 2 are both boys, how many outcomes are there for the third one? 2, which are what? Boy or girl. And this one? The same. And the next one? Same. And the next one? Okay. So what we have here, aptly called a tree diagram, lists every possible scenario that we might have when having 3 children, where we care about not just how many, but we care about the order. Now, how many scenarios are there? Well, there's boy, 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 so that's 1. Boy, boy, girl, that's the second one. And essentially, it looks like every one of these in the last one are the number of outcomes, right? So outcome 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes here. Agreed? Are all 8 of those outcomes equally likely?
Yeah.
Yes, all 8 of those outcomes are equally likely because our assumptions here are that a boy or a girl is 50% chance each. So every one of these branches is an equally likely branch across the board, which means every denominator before any simplification is going to be 8. And now all we have to do is ask ourselves, of these 8 outcomes, how many of them do not have any girls? Just one, the first one. How many of them have 3 girls? Just one, the last one. Those are the 2 you got right. How many of them have only 1 girl? 3. Boy, boy, girl. Boy, girl, boy. Girl, boy, boy. 3 of those 8 equally likely outcomes have 1 girl. And how many of those 8 equally likely outcomes have 2 girls? Also 3. Some symmetry here. 2 girls is the same thing as 1 boy. 1 girl is 2 boys. 50-50, it's got to be symmetric.
It's always gonna be symmetric.
Well, it's always going to be symmetric if it's 50-50,
Okay, based on these.
based upon the assumption of 50-50. Is it really 50-50? Apparently, statistically, it's not. Apparently, for evolutionary reasons, anyone know what's more likely, a boy or a girl? It's not that much off from 50-50, but you know what it is? It's actually boys are more likely, because historically, who is more likely to die earlier in life, a boy or a girl? Men. Why? Historically, not nowadays, but historically. We're fighting, we're always fighting, right? The men are off in war, and this is historical. This is not my, creation, but historically men, they're the ones who do the fighting in wars and whatnot. Women, of course, I'm not saying life is easy. Childbirth, historically, not the greatest experience. I'm sure it's still not great now. I wouldn't know, but I had a kidney stone a couple years ago, and it was the most painful experience of my life. So after it was over, I went online to find out how other people felt about the pain. And I found these various forums where all these men are saying it's worse than childbirth. And I'm saying, okay, it's great for a man to say that, but let's see what a woman has to say. And I kept scrolling down, and finally I found a woman. And she said, well, I've given birth and I've had a kidney stone. I'd rather give birth again. So, and yeah, so don't have one. Trust me on this one. It hurts. And you can have kids, but don't have a kidney stone. That you don't want to do that. All right, so anywho, any questions on that example? This is called a finite probability model. Why is this called a finite probability model?
There's a finite amount of solutions.
Close, there's a finite amount of solutions. Actually, it's finite number of solutions. The word amount is used for measurements that you can't, like an amount of milk, right? You can't say I put a number of milk into my cup. I put an amount of milk because it's a measurement. Number is for counting. So it's a finite number. So you can learn probability and how to speak good English, because we all speak English good here, right? Yes. Okay. So a finite number of outcomes makes it a finite model. Those are the easiest models to work with. The next easiest case is the discrete model, which is infinite, but at least you can count them. An example would be the basketball example before, right? How many basketballs it takes to hit, how many shots does it take to hit a basketball from full court? It could be 1 or 2 or 3 or 4. It goes up to infinity. It's not finite, but it's discrete because the outcomes are separate. You can count the outcomes. Okay, so this is both a discrete, actually is for both finite and countable. They're both under the umbrella of discrete. So this is a finite discrete model. Can anyone think of a model that's used, that we used already today? that's finite. We use it for a few of our examples. Dice, certainly a dice has a name. The dice example has a name. Oh, thank you. The dice example has a name. It's such an important model. Comes up in so many situations that it actually has a name. And what do I mean? It's not called the dice model. Dice is just a scenario. It's called the uniform model. Why is it called the uniform model? Because every outcome is as equally likely as any other outcome. So rolling a die, 1, 2, 3, 4, 5, 6. It's uniform across the board because all 6 outcomes are equally likely. Flipping a coin, heads or tails, uniform, 50-50. Having a single boy or girl, if it's 50-50, uniform, 50-50. Having 3 girls or 3 children and interested in the number of girls is not the uniform model because these numbers are not the same, right? They're different. You're front and center. You're just walking across the room. Did he not just walk across the room? You guys all saw that, right? All right. Now, what's an example of a continuous probability model that we've worked with either today? I mentioned it. One of our examples was continuous, or in a previous chapter.
So you said like waiting for a bus.
Waiting for a bus is a continuous model because the answer could be anything from now until whatever time. You subdivide the time into smaller and smaller increments. Technically, there's infinitely many. Yes. Well, continuous must be in. It's like magic. Continuous must be infinite, but infinite does not have to be continuous. The basketball model is infinite, but it's not continuous because the numbers are separated. But waiting for a bus is continuous. What's another example?
The time you wake up.
The time you wake up. That's another example of time, right? Time is certainly an example of continuous. What's an example other than time? Yes. No, I just did that. Yes.
Length,
Huh?
length.
The length of an object. I'm going to measure the height of the next person who walks into this room. The height could be anything from, whatever to whatever. Certainly, certain ones are more likely than others. But is that uniform? No, that's not a uniform model. It's continuous, but it's not uniform. Anything else that we've done earlier in the course that's continuous? Famous one? A point on a what? You mean I randomly pick a point, like I throw a dart at a dartboard type thing? Well, that's uniform, because in theory, every point is equally likely. Huh? Weight is not uniform, but we've talked about weight before. In fact, weights is an example of what I'm thinking of, as is height. We've used this a lot. We had a whole chapter dedicated to it. The normal probability model, the normal distribution is a probability model. No longer do we have to say what percent of people were between this and this. We can now say, if somebody walks into the room, what's the probability that he will be between here and here? And we answer it the same way, because since 18% of people are between here and here, there's an 18% chance that the next person will be between there and there. So the normal model is another continuous model. So we have the uniform model, the uniform, the normal. Yes? No? Maybe so? Is making sense? Is everyone lost? Am I speaking a foreign language? Yes.
You just said uniform.
Those are the only two continuous ones that we're going to be dealing with for a long time. At the end of the course, we get to one more called the chi-square. In a more advanced course, we do a lot more. We do the exponential, we do the downparts, we do the beta, we do the gamma, we do lots of them. And all these distributions are famous because they are useful. somewhere in life, somebody recognized that a distribution is important, and then it turned out that that distribution is important in lots of other places. So they gave it a name. Yes.
Is there also theta, vega?
Is there what?
Is there also theta, vega probability?
I mean, theta is a variable, but I've never heard of the theta distribution. But then again, this is not my field. So there could be lots of things that I'm not familiar with, but I've never heard of it. The beta is very important. The gamma is very important. The chi-square, chi is another Greek letter. Yes,
The only reason I ask, because those are all Greeks for options. I don't know if the,
I do know options. I studied them for a little bit.
is there any like reason?
I don't think there's any connection.
Okay.
Only 3 languages are used in math: English, Greek, and which one? Languages, dude, languages. English, Greek, and Hebrew are the only 3 languages that I know of, at least. When they're doing in logic, you will have the aleph no. This is the first letter of the Hebrew alphabet. Aleph, bet, gimel, alpha, beta, gamma. No coincidence there, yes?
Isn't the number system Arabic code?
The number system has Arabic derivations, but if you actually look at Arabic as it is today, we do not use any of those symbols in math that I'm aware of. I know we use English, obviously. We use Greek all the time, theta, so on. And Hebrew is used a little bit. Question so far. This chapter, chapter 11, is on probability. It's on the basics of probability, what probability is. It's an assignment, essentially, of a likelihood of an event occurring. Our goal is to assign likelihoods that conform with reality. If you come along and say, I believe the average height of the male 20 to 29-year-old American is 5'7". And I say, well, I don't think you're right. You might be right, you might be wrong. You know what? I'm going to take a test. I'm going to test 1,000 of them. I'm going to see what I get. Now, if I get as my result 6'2" as my average of those thousands, I might be very inclined to say, I think your 5'7" guess was wrong. Why would I say that? Because if 5'7" was right, we'd have a very little chance of getting an average of 6'2". And the fact that we did get that average means your assumption of 5'7" is very questionable. Does that make sense? This is the idea of the entire second half of the course. It's called hypothesis testing. I mentioned this on day 1. You come along, you say, I believe this. I believe result X. Someone comes along and says, well, let's test it. I got result Y. Is result Y close to X? Well, if it's close to X, then maybe you were right. I mean, I can't really imagine I get exactly what you said every single time. It's an experiment after all. But if it's close to X, then I can't say you're wrong. But if it's far away from X, I might start questioning your original guess, your original hypothesis. Well, how far do you have to be before you say this is too far? Well, we have to be far enough that the chance of being over here is 5% or less. Well, how do we calculate that it's got a 5% chance or less? By using the rules of probability. This is why we throw in this one chapter on probability just to give you the basics and to give you the understanding of what we're going to use later. We are not going to be deriving our formulas because the derivations are too advanced, but it's conceptual. If the results that we get has a very small chance of occurring under the assumption of your original hypothesis, we're going to question it. We're going to reject it. We're going to say this is probably not right. If the result that we got has a high likelihood of occurring, more than 5%, then we say, okay, maybe you're right. I don't have the evidence to reject it. Maybe you're wrong, maybe you're right. I don't know. We don't know the truth. We'll never know the truth. But either we get something close and we say, maybe you're right, I'm not going to say no, or we get something far away and we say, sorry, buddy, but I got to go with someone else. This is the idea of this entire chapter, okay? And why we're doing it at least. But in terms of the questions that you're going to be asked, nothing more complicated than this. Your questions are going to be very, very, very basic. I'm not going to ask you, for example, why in poker is a flush a better hand than a straight? Anyone here play poker? A little bit, más o menos. Why in poker is a flush better than a straight? By the way, in 3-card poker, a straight's better than a flush. But in 5-card poker, which is your usual poker, hold'em, etc., a flush is better than a straight. Why? Exactly. To get a flush with 5 cards is harder than getting a straight with 5 cards. But getting a flush with 3 cards is easier than getting a straight with 3 cards. So all of the hands in poker are all based upon probabilities. Why is this hand better? Because it's more rare. It's harder for it to happen. So all the hands from high card, a pair, 2 pairs, and so on, all the way through straight flush, royal flush, etc. It's all based upon the rules of probability. And the inventors of probability, the people in the 1600s who were the first ones to really investigate probability, were gamblers, or people that gamblers sent, mathematicians that gamblers asked questions to. They said, hey, I'm noticing this. I don't really understand why. Can you explain it? We're talking about Fermat. Anyone ever hear of Fermat? Fermat's last theorem? Nobody? Nobody? How about Pascal? Anyone ever hear of Pascal? Anyone know what Pascal's first name is? The coolest first name in the history of science. Blaise. Blaise. Well, actually, it's B-L-A-I-S-E, and I don't speak French or have any idea how to read things correct. Huh? Well, I still like Blaise, okay? So I'm going to go with that. So anyways, all probability comes from, historically, from questions from gamblers who were trying to, of course, increase their odds. Even in gambling today, the greatest gamblers make it very far in tournaments again and again and again. And if it's purely random, because the cards are in fact random, then why do the same people tend to get so far over and over and over again? There has to be some skill. And the answer is because those people have a deeper understanding of probability. I will play 10 hands. I know I'm only going to win one of them. If I'm at a table with 10 people, I can only expect to win 1 out of 10. I can't up that. So how do I last longer? No, I'm going to win 1 of 10. I mean, bluff is a whole other thing. Let's assume it just goes with the cards. Everyone stays into the end. Let's assume everyone stays into the end. No fold 'em, hold 'em. Everyone stays into the end. Okay, not necessarily all in, but everyone goes into the end. I'm only going to win 1 out of 10 hands. How do I make it further than everyone else? By maximizing how much I win on the hand that I win, and by minimizing how much I lose on the hands that I lose. I can't stop the fact that I'm only going to win 1 out of 10, but I'm not going to lose a lot on those 9 hands, and I will try to win a lot on that 1 hand. So they use the rules of probability to do this. Counting cards cannot be done in poker. It's impossible. Counting cards is a blackjack thing. In poker, you're not playing against the house. You're playing against people, and they reshuffle every hand. Counting cards, you're relying upon the fact that the shoe is used continuously for a number of hands in a row. Yes?
They'll use 3 decks of blackjack.
They use, I've seen 10 decks being used. There are places that only use 1. Very rare to find them. And again, why do they do this? Why do the casinos have the rules that they do? Because they understand probability. Okay, what we did today is the very basics. One of my favorite questions in probability When I first saw this question, I was like, how in the world would you even answer that? The question was, if you have a paper with infinitely many lines, equally spaced, and you take a needle and you throw the needle, and the needle lands somewhere on the paper, maybe the needle will cross the line, maybe the needle won't cross the line, right? What's the probability that it hits a line? You can actually calculate that with like 5 lines of math once you have the right math. It's a calculus problem, but with like 5 lines, you can answer that. Whereas on the surface, it's like, where do I even begin? The reason I find this stuff so interesting is because you can answer questions that it's just mind-boggling to even have a solution, let alone the solution is easy to find. Albert Einstein said, the most incomprehensible thing about the universe is that it's comprehensible. Think about that. Yes.
How do you know where it's going?
Because I saw the answer. If you asked me this before I've seen the answer, I'd be like, oh, but once I saw the answer, it's like, oh my God, of course, it's amazing. I once saw a proof that the shortest distance between 2 points is a straight line. Until I saw that proof, it was just like, well, it's obvious, of course. Then I saw the proof. I actually saw the proof. Beautiful. It's amazing, ingenious. And it was like in the 1800s. There's some amazing stuff out there. Anyway, this chapter, very, very basic. Okay, this chapter is about the rules of probability, conceptually what probability is, what makes a valid probability model, and some definitions like event, sample space, random experiments, and so on. We also have our basic rules. We listed all of the rules that we need for this course in probability, all 5 of them, and they seem pretty straightforward when looked at one at a time. And then you get to the homework and you're working on the homework and it's like, oh my God, what do I do? But when you work through it and you get to the answer, you're like, oh, okay, I see it in action now. It's really, really, really cool stuff. Other than that, there's a few other things in the chapter that we're not going to do. So that takes us to the end of chapter 11. We are going to skip after this to chapter 15. I'm also not going to give a quiz on 8 or 9 because those are not mathematical chapters, but we will have a quiz eventually on 11. And since we finished it today, the homework will be due next Thursday. And the quiz will be then on Thursday for chapter 11. Okay. Any questions on what we did today? Yes. A week from today. 8 and 9 is due a week from today.
8, 9, and 11.
8, 9 is due a week from today. 11 is due a week from Thursday. Okay. If you came late and you want credit for being here, now's the time to let me know.